So hello everyone, welcome back to my YouTube channel. So today we'll be starting with the subject mathematics and we'll be studying vector spaces today. So what are vector spaces? Vector spaces are a non-empty set. Let's assume a non-empty set V is said to be a real vector space if there are defined two operations that are called vector addition and scalar multiplication denoted by plus and dot symbol respectively, such that for all u, v, w belonging to the vector space and a comma b belonging to the real space, the following 10 properties should be satisfied. These 10 properties are very important and they have to be memorized in order to solve the questions related to this topic. So now let's try doing one question and we'll get a fair idea of what these properties are and how to apply them. So this is our first question. Show that the set R of real numbers is a vector space with respect to two operations. One is your addition. We just now had written one is vector addition and the other is scalar multiplication. Now here we have to satisfy all the 10 properties. So let's start solving. So let u v w, I'll not be writing that. I'll dictate that. Let u v w be members of the vector space and a and b be two real numbers. Then we'll start solving first. Real white closure property. Closure property states that u plus v is equal to u to the power 5 plus to the power 5 to the power 1 by 5. This is belonging to R as we can see in here. So second, commutative. U plus V is equal to U to the power 5 plus V to the power 5 1 by 5 is equal to V to the power 5 plus U to the power 5 1 by 5 is equal to V plus U. If we write V plus U, we'll write like this and U plus V like this. But is A plus B whole square equal to B plus A whole square? Yes, it is. So therefore, these two expressions are also equal. So next property is your associative property. Associative property states u plus v plus w is equal to u to the power 5 plus v to the power 5 raised to power 1 by 5 plus w is equal to u to the power 5 plus v to the power 5 plus, no, there's an error here. Let me correct it. So this will be u to the power 5 plus v to the power 5 plus w to the power 5 whole raised to power 1 by 5. And when we say u, let's erase the brackets, u plus v plus w, it will be equal to u to the power 5 plus v to the power 5 plus w to the power 5 raised to power 1 by 5. So as we can see here, you can also write this in the form u plus v to the power 5 plus w to the power 5 raised to power 1 by 5. So as we can see, they both are equal. If you see here, w to the power 5 into 1 by 5 will be w. So therefore, associative property will also get satisfied here. Next, fourth property. Your fourth property is existence of identity. Now, in existence of identity, we say 0 belonging to R. Therefore, u plus 0 is equal to u to the power 5 plus 0 to the power 5 raised to power 1 by 5 is equal to u. And 0 plus u will similarly be equal to this only, u. Because when we take 0 plus u, it will be 0 to the 5 plus u to the power 5 raised to power 1 by 5 is equal to u. So we get same expression, therefore u plus 0 is equal to u is equal to 0 plus u. Therefore, property is satisfied. Additive identity. Next, existence of inverse. U plus minus u is equal to u to the power 5 minus u to the power 5 raised to power 1 by 5 is equal to 0, which will also be equal to minus u plus u. Therefore, minus u is additive inverse of u. We'll write therefore minus u is additive inverse of u. Sixth one says any scalar multiplied by the u, you will get a raised to power 1 by 5 into u. This is also belonging to R. Seventh, a into u plus v will be a u to the power 5 plus v to the power 5 raised to power 1 by 5. Then we have a property, multiplication property, that is a into u is equal to a to the power 1 by 5u. This was a property. So by this property we get a raised to power 1 by 5 u raised to power 5 plus v raised to power 5 raised to power 1 by 5. Further we can write it as a raised to power 1 by 5u plus a raised to power 1 by 5v is equal to au plus av. How? Reverse of this conversion. So therefore, we have seventh property is also satisfied. Now a plus b into u, a raised plus b raised to power 1 by 5 u, a u raised to power 5 plus b u raised to power 5 raised to power 1 by 5. How the power of u getting inside is 5. 5 into 1 by 5 gives back u. Therefore, we are putting u to the power 5 inside. So after this you have a raised to power 1 by 5 u plus b raised to power 1 by 5 u. So this can be further converted to au plus bu. So eighth property is also satisfied. Ninth property. Ninth property states that ab into u is equal to ab raised to power 1 by 5 into u. Multiplication identity that was given in the question. Now this can be further written as u. Now separate them. A b raised to power 1 by 5 u. Now a raised to power 1 by 5 u is equal to a into bu. A raised to power 1 by 5 is so is equal to a b u. So this is also satisfied. Then 1 into u is equal to 1 raised to power 1 by 5 into u is equal to u. Hence, R is a real vector space. Space as all 10 properties are satisfied. So next now. So this is your homework question. Property 8. What is property 8? A plus B into U, this property, it will not be satisfied here. Let's try A plus B raised to power 1 by 5 U was earlier. Now we are saying when any scalar is multiplied. So A into U is equal to AU. So here AB into U will be similarly ABU. A plus B into U, it will remain the same. Then after this, now there's a plus identity here that we can follow. No. So now A raised to power 5 plus B raised to 5 raised to power 1 by 5 into U. So now when U gets inside, we saw that it will become A raised to power 1 by 5 U plus B raised to power 1 by 5 U. Now here we see A into U is equal to A into U, AU. So A raised to power 5 into U plus B raised to U. So we should have got A plus B into U as AU plus BU, but we are not getting that. Therefore, its property is not satisfied. Earlier we had A into U gives A raised to power 1 by 5 into U. That's why we could interconvert them and get the answer. But here it's not possible because AU to U here is AU, this property. Earlier it was AU is equal to A raised to power 1 by 5. Now let's start with subspace. So if V is a vector space and W is a subset of V, then such that W is also a vector space under the same operations as in V. So W is a subspace of V. So now let's understand this with an example. So verify whether W, where x comma y, where x minus y is equal to 0, such that x and y belong to R, is a subspace of R square. Now what do we mean by R square? X comma y in this form. So let U is equal to x1 comma x2, V is equal to y1 comma y2, and it's belonging to W. Let's assume that and an A belongs to R. So according to W, x1 minus x2 will be equal to 0 and y1 minus y2 will also be equal to 0 as they belong to W. Therefore, U plus V will be x1 comma x2 plus y1 comma y2 is equal to x1 minus x2 plus y1 minus y2 is equal to 0. Therefore, now how is it equal to 0? Some may ask. So x1 minus x2 is 0, y1 minus y2 is 0. 0 plus 0, 0. Now we have A into U is equal to A into x1 comma x2 is equal to A of x1 comma A of x2. So does this belong to W? So if we have 4 minus 4, let's say 4 minus 4 is equal to 0. If we multiply 2 to each, will it still be equal to 0? Yes, it will be. So it belongs to W. Let's erase this. Now since ax1 minus ax2 is equal to a of x1 minus x2 is equal to a into 0 is equal to 0. Therefore, W is closed with respect to vector addition. Vector addition we had seen. vector addition and also scalar multiplication. Hence, W is a subspace of R square. So next question. So next question is a matrix question. It says PS into QR delta is not equal to 0, a determinant basically. How do you see that? When you take the determinant, PS minus QR is the determinant value. So M22 means a matrix of X, Y, Z, W's. For 2 into 2 matrix. Let's erase this. So delta is not equal to 0. So let's assume let U is equal to 1, 0, 0, 1. Here 1 minus 0 delta is equal to 0. Is it equal to 0? No. It is equal to 1. That is what a property says, that it should not be equal to 1 is not equal to 0. And V let's take it as minus 1. So this will be equal to minus 1, which is not equal to 0. Therefore, they both belong to W. This also belongs to W. So U plus V is equal to 1, 0, 0, 1 plus minus 1, 0, 0, minus 1. This comes out to be a 0 matrix, which does not belong to W. Now, since it is a singular matrix, therefore, W is not a subspace because it violates the property. Subspace of M22, that is 2 into 2 matrix. Next. This is your homework question. So basically it is saying let W1 and W2 be two subspaces of vector space V. Show that W1 intersection W2 is a subspace of V. Now since W1 and W2 are subspaces of V, so at least the zero vector will lie in their intersection. Therefore, we can say zero vector will be there. Therefore, W1 intersection W2 is not equal to phi. Now, we assume let U, V will belonging to their intersection and your A, B is belonging to R. So now A into U plus B into V will also belong to W1 and your A into U plus B into V will also belong to W2. And since W1 and W2 are subspaces, therefore A into U plus B into V will be belonging to W1 intersection W2. This shows that it's a subspace. Now next part says give an example to show that W1 union W2 need not be a subspace. So your example is, let's say, this is your homework question, but I'll explain it. So let's say I take the first one as x1 comma 0 and second one is x2 comma 0 and they both are belonging to, so this one is W1, this one is W2, W1, W2. You'll write x belonging to R, that you'll write. So what whole will be 1 comma 0 plus 0 comma 1. What will this be equal to? 1 comma 1. Now 1 comma 1, does it belong to any of the W's? Does it belong to the intersection? No. Therefore it's violating. So it's not closed with vector addition. Therefore not a subspace. Second part. Third part. We are saying show that W1 union W2 is subspace. if either W1 is a subspace of W2 or W2 is a subset of W1. So if this happens, if W1, therefore W1 union W2 will be equal to W2, and in this case W1 union W2 will be equal to W1, but they both are subspaces of V, and therefore we can say that it's a subspace. Now you see, it's equal to W2, it's equal to W1. And does it belong to them? Yes, it does. So we can say that it's a subspace. But try to understand the question carefully because this will not be the final answer, and that part will be your homework. And I'll give you a hint. The hint is addition is equal to V. Let me erase it. Is equal to V. So it belongs, does it belong to W1? Is there any problem that is occurring here? This is what you'll have to find out. I've solved all the three parts, but the third part is still incomplete. So you have to solve it. So next is span of a set. Let S be any subset of vector space V, then set of all linear combinations of infinite number like alpha 1 u1 plus alpha 2 u2 and so on till alpha n un of finite number of members of S. Yes, so this member's finite number of linear combination is called the span of S and is denoted by span of S or L of S. It is mentioned here. Therefore, now this is the representation. So let's solve one question to have a better understanding. So show that the span of 2, 3, 4, 1, 5, 7. Now first of all, when you get this type of a set, try to write it as 2, 3, 4, alpha 2, 1, 5, 7 plus alpha 3, 3, 11, 13 like this. So we can say therefore 2 alpha 1 plus 1 alpha 2 plus 3 alpha 3, then 3 alpha 1 plus 5 alpha 2 plus 11 alpha 3, then 4 alpha 1 plus 7 alpha 2 plus 13 alpha 3. Now try to put it as a matrix 2, 1, 3, 3, 5. We are arranging the coefficients 4, 7, 13. Now when you use suitable row operations like we used to do, like R3 gives R3 minus 3 R2 and R1 gives R1 minus 2 R2. Similarly, on performing these operations, we'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. So this is a one identity matrix that we have got. So we can say that alpha 1 into 1, 0, 0 plus alpha 2 into 0, 1, 0 plus alpha 3 into 0, 0, 1 is the span of S. Let me write the representation for you. Is the span of S where alpha 1, comma alpha 2, comma alpha 3 belongs to R. So this is the representation. So this is how you solve the question. First of all, alpha 1 u1. Either you can solve it this way, a1 b1 whichever you feel comfortable. I feel comfortable in alpha 1 U1, so I follow that convention. So this is how you solve this question. So now next question, find the simplified span of set x cube minus 1, x square minus x and x minus 1 in a polynomial of power 3. So let's see. Here we can arrange the exponents. I'm using white pen. Here we can arrange the exponents. Here let's arrange the exponents in form of a matrix. So now x cube 1, 0, 0 and not. First let's put it horizontally. So 1, 0, 0, minus 1. So x cube and minus 1. Then 0, 1, minus 1, 0. X square, x cube, x square, x and constant. So now here we'll have 0, 0, 1, minus 1. So when you will solve this, you will get it as 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 1, minus 1, minus 1. So therefore you can write it as L of S is equal to alpha 1 into x cube minus 1 plus alpha 2 into x square minus 1 plus alpha 3 into x minus 1, where alpha 1 comma alpha 2 comma alpha 3 belonging to R. If this pen is not visible, let me use white pen. So how will you do this part? See, these two columns are same. So something is going on in these two. So what we'll do is R3, C3, column 4 is column 4 minus column 3. Perform column operation. So column 4 minus column 3 gives you minus 1. Column 4 minus column 3 gives 1. And column 4 minus column 3 gives minus 2. And similarly, when you will solve this, you'll get this. Try to perform the best operations so that it gets simplified. Either you can apply row operations if you don't have 0, 0. Here we have 0, 0. That's why we did column operations is 0, 0, 0. So next question is find the simplified span of these. Matrix of 2 into 2. Now we can write them in a format like alpha 1 minus 1, 1, 0, 0. Alpha 2, 0, 1, 0, minus 1 plus alpha 3 minus 1, 0, 0, 1. If we write them in a single matrix, it will be minus alpha 1 minus alpha 3, alpha 1, alpha 2 minus alpha 2 plus alpha 3. So now for simplified span, we write each matrix as continuous row vector. So minus 1, 0, minus 1. So let's see how are we writing this. So you can write the first matrix as minus 1, 1, first row, then second row. Similarly, next one as 0, 0, 1, minus 1. Third one as minus 1, 0, 0, 1. Now arrange them in a horizontally. So 1, minus 1, 1, 0, 0, plus 1. So here 0, 0, 1, minus 1, then 0, 0, 1. So when you'll apply column operations, you'll get 1 0 0 0 1 0 0 0 1 minus 1 minus 1 minus 1. Then you will be able to write them as I'll write them here because I have space here. So 1 0 0 minus 1, then 0 0 1 minus 1, second one, and 0 1 0 minus 1 in this form. And then after that you'll form the correct expression. I'll erase all of this now and I'll write the final answer here in green. So answer will be A, C, B, minus A, minus B, minus C. This is the answer. We are taking A as alpha 1, B as alpha 2, and C as alpha 3. So you can match your answer from this. So now let's go on to the next question. This is basically how you'll solve the question. When you get these matrices, you club them together in this form that we had written. Just simple addition you have. Now let's start with linear independence. So what is linear independence? A finite non-empty subset S of a vector space V is said to be linearly dependent if and only if there exists real numbers and not all zeros such that this sum is equal to 0. If S is not LD, this sum is equal to 0. That means all the values of alpha 1, alpha 2 are equal to 0. Then it's said to be linearly independent, Li. And linearly dependent, LD. These are very commonly used terms that we use. So let's see our examples. So this is our first example where it's saying the set S 1, 2, 2, 4 is in LD, linearly dependent in R square. So 1, 2, 2, 4. So alpha 1 U1 plus alpha 2 U2 is equal to 0. So alpha 1, 2 alpha 1 plus 2 alpha 2 plus 4 alpha 2 is equal to 0, 0. So we get two equations. One is alpha 1 plus 2 alpha 2 is equal to 0, and 2 alpha 1 plus 4 alpha 2 is equal to 0. Therefore, we are getting a single equation alpha 1 plus 2 alpha 2 equal to 0. So we have non-trivial solution. Let's say your alpha 1 is equal to 2 and alpha 2 is equal to minus 1, plus 2 and minus 1. Therefore, this set is in LD. This set is LD. LD, linearly dependent, not 0. If alpha 1 and alpha 2 were 0, we could have said that they are linearly independent. So next one now, it is saying verify whether this set is Li. So Li, how will we prove that? In matrix format. So 3, 1, minus 1, minus 5, minus 2, 2, 2, 2, minus 1 equal to 0, 0, 0. So let's form an A augmented B matrix. Write the equations, then form the augmented matrix. You will get this minus 5, 2, minus 2, 2, and 2 minus 1, 0, 0, 0. So basically, when you solve it, you get 1, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 0, 0. Therefore, we can say that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to 0. When you put the values alpha 1, alpha 2, alpha 3, therefore Li linearly independent in R cube. Now next is basis. What is basis? A subset B of vector space V is a basis if B is Li and L of B is equal to your vector space, that is span. We have earlier said span L of S is equal to your span. Therefore, the basis set B, the span of B should be a vector space. Span of B should be equal to V, vector space. The basis set B is Li and generates or spans the vector space V. So we have an example. So before that, let me solve another example. I'll give you a simpler question. So first, let's assume the set, let's say B is equal to 1, 0, 0, 1 is a basis in R square. So alpha 1, 1, 0 plus alpha 2, 0, 1 is equal to 0, 0. Therefore, we get alpha 1 is equal to alpha 2 is equal to 0. Therefore, we can write alpha 1 comma alpha 2 is equal to alpha 1 into 1 comma 0 plus alpha 2 into 0 comma 1. This is how you write it. And so we can see that it's a linear combination of members of set. So this is the basis. Next, we'll study dimension, and dimension is calculated on the basis. Whatever you get in the basis, then you calculate the dimension. So now we'll take up this example. So in this example, it will be difficult to directly solve like this in case of alpha 1 plus alpha 2. So matrix. Matrix is a savior. So 2, 3, 1, minus 1, 2, minus 3. So using your transformation, you'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. Whenever it's an Li, you mostly get that only. So L of B is equal to alpha 1, 1, comma 0, comma 0 plus alpha 2, 0, comma 1, comma 0 plus alpha 3, 0, comma 0, comma 1 such that alpha 1, comma alpha 2, comma alpha 3 belong to R. Therefore, B is a basis of R cube. Why? It can be represented in form of a linear combination. Linear combination. As we can see the number of sets that we have here. In form of a linear combination, we can represent the span of this vector space. So this is what. Now this is one example that I have already solved. This is a solved example. The set B1 x square for self x raised to power n is a standard basis of p raised n is polynomial function. So any polynomial of x in degree n is of course a linear combination. So your B contains 1 x square till x raised to power n. So your span of B is your polynomial set. So your B is an Li as their multiplication will be equal to 0, and this will give alpha 1 alpha 2 till alpha n equal to 0. Therefore it is a basis, standard basis. So now let's study dimension. The number of elements in the basis is called dimension. So here, so we have how many? 1, 2, so 2. 1, 2, 3, 4. So 4. This is basically our dimensions. In the earlier question, where we had, let's say, I'll take an example, alpha 1, 1, comma 0, comma 0, alpha 2, 0, comma 1, comma 0, alpha 3, 0, comma 0, comma 1. What will be the dimension here? 3. So this is what I mean to say by dimension. This is an extension when you calculate the basis, it could be asked. So thank you all. This was all about vector spaces. We studied the 10 axioms to prove it's a vector space. Then we studied subspace. Then we studied span set. Then after that, we studied basis and dimension. So thank you. If you like the video, do like, share, comment, and subscribe. And if you have any doubt regarding these topics, you can write them down in the comment section. So thank you. Have a great day.